good day. My name is Mhlanga and I'm actually from RustMD campus. Today we'll be looking at power machines and 5 velocity diagrams. Right. Basically, velocity diagrams depicts what will be actually happening in the steam turbines as the steam passes through the turbine. And it's actually another way of calculating the power required, the axial thrust, and all this stuff like that. So we do velocity diagrams in order to find the power required and the axial thrust. So now we have 3 types of velocity diagrams. We have velocity diagrams for turbines that have got axial thrust. Then we have velocity diagrams for turbines that do not have axial thrust. Then we have velocity diagrams for turbines that discharge axially. Right. On the board here, I have the cross section of the blade of a turbine. At the top there, I have the position of the nozzle. Right. As the steam leaves the nozzle, it enters into the blade at an angle of delta I. At an angle of delta I. And the speed is AI. And the angle of the blade will be actually beta I. The speed of the blade will actually be B. Right? So the steam goes into the turbine blade at an angle of delta I and at a speed of AI. It glides through the blade and goes out at an angle of delta E and a speed of AE. Right. Now, at the top here, we have the velocities at inlet, where delta I is the angle at inlet, or what we call the nozzle angle. Then AI, the speed of steam as it leaves the nozzle, or the speed as the steam as it enters into the blade. Then B is actually the blade speed, which is actually going to be the peripheral speed of the blade. Then whenever we have 2 things moving, we say the other one is moving relative to the other. So the steam is moving relative to the blade, or the blade is moving relative to the steam. So we have relative velocity at inlet, which is going to be Ri. Right? Since our velocity is actually at an angle, drawing a horizontal component of that velocity is going to give us what we call well velocity at inlet, which is going to be from here to there. This is going to be well velocity at inlet, which is Wi, right? And the vertical component of that velocity of the steam at inlet is Fi, which is actually flow velocity at inlet. Flow velocity at inlet. So that actually completes the inlet side. Now coming to the bottom here, we have our steam leaving at AE, which is actually the exit speed of the steam. And the angle at which it leaves the blade is going to be delta E. Then drawing a horizontal component for that velocity there, we are going to have what we call well velocity at outlet, which is going to be WE. Then the vertical component of that same velocity there is going to be our flow velocity at outlet, which is going to be FE, flow velocity at outlet. Right? Then again, we are saying this steam is moving relative to the blade. This is still the blade speed from here to there, which is going to be the same speed from there to there. So we are saying the speed at outlet, the steam speed at outlet is relative to the blade speed at outlet as well. So we have relative velocity at outlet is Re. Right now, that actually completes the outlet velocity diagram. Now, combining the two, the inlet and the outlet, we come up with a complete velocity diagram, where now our nozzle will be actually here. And it will actually be discharging into the blade of the turbine at an angle of delta I. And the steam will be leaving at an angle of delta E. And at a relative velocity of Re. And at a relative speed, this one is this one is actually AE. And this is R E, because the relative speed is going to be the speed at outlet relative to the speed of the blade. Then the speed at inlet relative to the speed of the blade is going to give us relative velocity at inlet, which is going to be Ri. And this is going to be flow velocity at outlet and flow velocity at inlet. Then Wi represents the flow velocity at inlet, which is going to be from here to there. Then We represents the flow velocity at outlet, which is going to be from here to there. That completes our velocity diagram. Now, we want to see actually why we do velocity diagrams, right? We do velocity diagrams in order to calculate the power developed. The power developed by the turbine, which is going to be given by mass times wall velocity times the blade speed. And this is actually going to be, our mass is going to be in kgs per second. Then this is going to be watts. Then we also do velocity diagrams in order to calculate our axial thrust. And axial thrust is going to be given by the mass into Fi minus Fe, which simply means the mass into flow velocity inlet minus flow velocity at outlet. Then we also do velocity diagrams in order to calculate the diagram efficiency. Which is sometimes called the blading efficiency. The blading efficiency. And this is actually going to be equal to 2WB over AI squared, which is 2 into the wall velocity, total wall velocity. This W is actually representing total wall velocity, which is WE plus WI. So it's going to be 2W into B over the velocity at inlet squared. Then we also do velocity diagrams in order to calculate the force on the blades, the driving force. We also do velocity diagrams in order to calculating the driving force, which is going to be given by MW. Right. Now we want to relate especially the axial thrust to these three that we have at the top there. We are saying axial thrust is equal to M into Fi minus Fe. Now, if a velocity diagram is actually for an impulse turbine, which has got Fi not equal to Fe, it simply means there's going to be axial thrust developed because this is not equal to that. So if this is not equal to that, so it simply means there's going to be axial thrust developed. But however, if it's actually a velocity diagram for a turbine that does not have axial thrust, it means therefore that Fi should be equal to Fe. So that if you say Fi minus Fe is going to be 0 here. So what does it mean therefore in our velocity diagram? It simply means therefore that the point, let me just name these points A, B, C, D, E, and F. So what does it mean therefore that? What it means therefore is that the point D and the point E should actually be on the horizontal, on the same horizontal plane when it's actually for a velocity diagram for no axial thrust. Why? Because this Fi will be equal to Fe. And Fi and Fe are actually measured from this point straight to the top there, and this one is measured from that one to the top there. So now what it simply means is these two have got to be on the same point. For the velocity diagram for the axial discharge, the velocity diagram will look like this. We are saying delta E is equal to 90 degrees. So it will be looking like this. And this angle there will be 90 degrees, which means therefore that this AE is going to be equal to RE, to FE. AE is equal to FE. So in other words, if this is going to be 90 degrees, It means therefore that this one and this one will actually be on the same point and on the same line. Right, basically that explains the three types of velocity diagrams that we have. We said we have velocity diagram for axial thrust, which will actually have Fi not equal to Fe. We said we have velocity diagrams for turbines that do not have axial thrust, which means Fi and Fe will be actually on the same horizontal point. Then we said we have velocity diagrams for axial discharge, which means our delta E is going to be 90 degrees. On the board, we have a question that says, or that reads, the average blade speed of an impulse turbine is 300 meters per second. The relative velocity of the gas is 600 meters, and the blade inlet angle is 20 degrees. Friction causes 5% loss in the velocity as the steam moves over the blades. The turbine does not develop axial thrust and uses 90 kg gas every minute. Use a scale of 1 centimeter equal to 50 meters per second and construct a velocity diagram. And that's 1.1. And 1.2 reads, determine the following from the diagram. 1.1.2, the exit angle of the gas, 1.2.2, the inlet angle of the gas, 1.2.3, the exit blade of the exit blade angle, sorry. Then 1.2.4, the power developed, 1.2.5, the diagram efficiency. Now we want to see how we actually draw this velocity diagram. But however, before we start drawing the velocity diagram, let me just explain something on the 5% loss. Now you are going to realize that as the steam enters into the blade, it's going to incur some frictional losses as it glides over the blade. So what it simply means therefore is that the outlet relative speed is not going to be equal to the inlet relative speed. So how do we find then, or what's the relationship between the outlet relative speed and the inlet relative speed? The relationship between the two is that Re, being the outlet relative speed, is equal to K Ri, being the inlet relative speed. Now, what it simply means is that this K now takes into consideration the frictional losses that take place, which simply means therefore that K is the friction factor. Is the friction factor. So that is the relationship between the relative velocity at outlet to relative velocity at inlet. Our relative velocity at outlet is always going to be less than the relative velocity at inlet because of the frictional forces, unless probably if frictional losses are actually negligible. So it means Ri is going to be equal to Re. Right, now let's go to the velocity diagram. What I will actually encourage you to do is to draw a skeletal velocity diagram of what actually is happening there. Putting into the velocity diagram that we would have drawn these values that you have here. So I'm going to use this diagram that I have here to put in those values that we have on that question. Now the question is saying the average blade velocity of an impulse turbine is 300 meters per second. So what we mean by average blade speed is our B. So our blade speed is B, which is going to be 300 meters per second. I put my 300 meters per second there. The relative velocity of the gas, they are actually emphasizing on the relative velocity of the gas. So that now becomes our Ri, which is going to be equal to 600 meters per second. All right? And the blade inlet angle is 20 degrees. Right? At point B here, that's where we have blading angle. Our beta I represents the blade inlet angle, and beta E represents the blade outlet angle. So now they are saying the blade inlet angle is 20 degrees. So that means our beta I is equal to 20 degrees. Please take note. Our relative speed starts from the nozzle, it goes to B, then going out there, it's going to be Re. Then at point A, we have steam inlet and steam outlet. So at point A, we have nothing to do with relative velocity. At point B, we have nothing to do with steam. So at point B, we are talking of blading angles. Beta I representing the blading angle at inlet, beta E representing the blading outlet angle of the blade, sorry. Now, they are saying friction causes 5% loss. We are not interested in the losses. We are interested in what actually happened. So our K factor now becomes 100% minus 5%, giving us 95%. So our K is equal to 0.95. Our K is equal to 0.95. 5% loss in the velocity as the steam moves over the blade. The turbine does not develop. The turbine does not develop. Please underline this. The turbine does not develop axial thrust. So basically what it points to is that we are going to look at a velocity diagram that does not develop axial thrust. So in other words, our Fi should be equal to Fe for us not to have axial thrust in the turbine. So in other words, we are saying here, Fi is equal to Fe and uses 90 kgs of steam. This 90 kgs now becomes our M equal to 90 kgs. Gas per minute, please write per minute, is very, very important because when we are now calculating our power developed, when we are now calculating our axial thrust, when we are now calculating anything that has got to do with calculations, it's going to be kgs per minute. So we are going to be converting this from kgs per minute to kgs per second, right? Now they are saying use a scale of 1 centimeter equal to 50 meters per second. Use a scale of 1 centimeter equal to 50 meters per second. Right, the first question that comes into your mind is, where do I start? We always start from our line FC. We always draw our line FC first, which is going to be drawn horizontally and in landscape form. Horizontally and in landscape form. Now, where to start will actually depend on the data that you have been provided with. Now, in this case, you are going to realize that we don't have anything that relates to A except 300 meters per second. But for B, we have 600 meters per second and 20 degrees. So our starting point is going to be B. So now, let's mark our point B. This point B should be more on the right than onto the left because our diagram is going to be more inclined to the right than it's going to be on the left. So now, what it simply means is we are going to measure 20 degrees anti-clockwise at B. 20 degrees anti-clockwise at B, which is this 20 degrees. So I'll put my protractor like this, then I'll actually mark my 20 degrees. Clockwise like that. Then I'll draw a line passing through that what? I'll draw my line passing through that 20 degrees. Unfortunately, this is not going to be exactly what we need because, right, I'll draw my line passing through that 20 degrees, right? Then the scale is saying 1 centimeter equal to 50 meters per second. Then it simply means we are going to divide this 600 meters per second by 50, which means it's going to be 30 centimeters, is it? Oh, no, 1 here, 50 over 50, this is going to give us what? 1, 2, 12 centimeters. So this is going to be 12 centimeters. So it means from B there, I'm going to mark my 12 centimeters. Let's say my 12 centimeters is somewhere there. Then I mark at that point there. That's my 12 centimeters. Then what it simply means therefore is that since I don't have this speed AI, the speed at inlet, since I don't have this speed at II, what it simply means is I now have point D by virtue of having this point there. So what I have to do is to actually draw this line from here to there. But what I will actually use to draw that line is I have to actually draw a horizontal line first. Why? Because we are saying Fi is equal to Fe, and our flow velocity should be on the same horizontal line. So how do I do that? I will actually put my protractor here. I will make sure that this 20 degrees here is coinciding with this line that I drew there. So that the line that I'm going to draw at 0 degrees here, at 0 degrees there, I will mark it, this should coincide with the 20, but what I want is 0 degrees, so that I'm going to draw a horizontal line there. So I'll actually draw the horizontal line through that 0 from that point there. Unfortunately, it's not passing through the point there. It's not going to be horizontal there. It's not going to be horizontal, but this should be actually somewhere here, 20 degrees there. You draw a horizontal line there. Sorry. You draw a horizontal line there. Right. This horizontal line is simply saying what FE you have to have here should be on this line. Right? Now, how do I find that other point? I have this point here, or this velocity there, and I have my K there, and I have a relationship of this relative velocity to this relative velocity, and that relationship is RE is equal to KRI. So what therefore I have to use is this 600 meters per second and this K to find this one. Then I'm going to draw a line from B to cut this horizontal line somewhere, right? Which simply means therefore that I'm now going to say 0.95 times 600. Times 600, 30. Unfortunately, I had not calculated that. 30, let me see, 60. 30, 6 times 9, 54 plus 3, 7, 6, 0, 5, 0, 0, then we put, so 570. And this is going to be 570 meters per second. This is going to be 570 meters per second. Right? We're saying RE is equal to KRI, which is going to be 0.95 times 600, which is going to be 570 meters per second. Right? Then I divide this 570 meters per second by 50. This RE is giving us 11.54. Right? What it simply means therefore is that I'm going to draw a line from this point to cut this one at 11.54. So I'll put my ruler like this. This has got to be at 0. This has got to be at 0. So I'll put it like this, then slide it until the 11.54 crosses this line. Say it crosses it there, somewhere there. So I'll mark that point there. Then I'll draw this line straight to there. Right? How do I find my point A? My point A is actually given by 300 meters per second. So this 300 meters per second is going to be divided by 50, which is going to be about 6 centimeters. So I'm going to mark from here to there, 6 centimeters. So that's going to be my A, 6 centimeters from here to there, because it's 300 meters per second. Then I'll draw my line from here to cut it there. Then I'll complete this drawing by drawing a vertical line to cut that one there, draw a vertical line to cut that one there. That completes our velocity diagram. That completes our velocity diagram. So now everything that we are supposed to calculate, the exit angle of the blade or the exit angle of the gas, you are going to actually measure this angle. Measure this angle from here anti-clockwise to guide that exit angle of the gas. Then the inlet angle of the gas, you also have to draw this line to A. You also have to draw this line to A. So for the inlet angle of the gas, you measure this line from there to there. This one is measured anti-clockwise, this one is measured clockwise. Then the exit blade angle, you are going to measure this one from here anti-clockwise to there. Then the power developed, like we said previously, power developed is equal to MWB. Then they are now saying the diagram efficiency or the blading efficiency. This diagram efficiency is sometimes referred to as the blading efficiency. And we said blading efficiency is equal to, is equal to 2WB over AI squared. Then you will be actually done with your velocity diagram. But please take note, in this velocity diagram, you have to actually label it in meters per second. So this is going to be 600 meters per second. This one here, 300 meters per second. So this one, you actually have to put it, Fi is equal to, Fe is equal to, AE is equal to, delta E equal to, Re equal to, then you measure from here to there to have WT, which is the one that you're going to be using all here. And please don't forget to convert your M into kgs per second. I hope we've covered everything that we have to cover. And I hope this is going to be helpful to you. Thank you.